Okay, there we go. So, lecture 4-6, the last actual lecture of new material. Transient DC motor performance. So, in the last lecture we did, so lecture 4-5, we did steady state DC motor performance. And we started with a discussion of how the model for that situation is very specific. There's a specific test, I guess, situation or test environment that you use to characterize the steady state performance of a motor. And so we did that model. It was slightly different than the model that we had talked about in the preceding lecture, which was lecture 4-4. In this lecture, we're going to go back to the model of 4-4, which is the model of the apparatus in the lab, right? So in the lab, we have the motor and the flywheel with the external bearings on it, and the one that you did the tests on last week in lab. So that's what we're going to go back to here, and we're going to examine it in transient response. And we're also going to learn how to learn a couple things, well, actually how to estimate a couple parameters of the system from the data that you gathered in lab. So that's our goal today, is to get through all of that material. So it's once again in MATLAB that I'll do the analysis here. So all the code here is MATLAB code. Feel free to get on the text website, and there's a source code page on there that has this, all of the source code for this lecture in MATLAB format.
What was that?
So it's on the text web page. So if you go to texts, and you go to dynamic systems, and you go to the source page, then what we have is not listed. I don't think this is it. No. Huh. Well, it's up there. It's just not listed here in this list. So I'll upload that after this lecture, but it'll show up in this list. It'll say something like transient DC motor electromechanical.
It's under dynamic systems.
Yeah. So, yeah, glad I checked. So, okay, so we've got this this MATLAB code, and you can also copy and paste it from this PDF too. It's fine. So we define parameters. That's how we begin again, which is how we began the last lecture. But there are a couple things a little bit, I guess, in addition to what we did last time. The flywheel parameters are coming into play now. So we have to compute what the moment of inertia is of the flywheel. And then also the bearing damping, not the motor bearing damping, but the external bearing damping. So otherwise it's the same as we did before. And what we're going to do is we're going to form a state space model in MATLAB, and we're going to simulate this thing, okay? So this is the first time we've actually seen this, and it's so easy. I feel like I should have shown you earlier because it's so easy to do. Okay, so what we do is we just define our A, B, C, and D matrices, which were defined in lecture 4-4, so we already have them. We just write them out in MATLAB code. I use lowercase a, b, c, and d because I've been around the block once or twice, and let me tell you, bearing damping B and capacitance C, it's almost impossible not to use capital letters for those. So for my A, B, C, and D matrices, I always use lowercase when I code them up. It helps. Otherwise, you'll get some errors, and you'll be like, what? I don't understand this error. This doesn't make any sense. And then you'll remember me telling you this, and you'll be like, oh, that's why. That's just my fantasy. I don't know if you guys will actually have that happen, but
Can you use MATLAB more in next semester?
yeah, a lot. I hope you like it. I was using Python when I was teaching this last year, and then people hated it, so I went to MATLAB. So I like Python. I think it's cool, but there's a little bit more of a learning curve that's more difficult, I guess. So then there's this line. So A, B, C, and D, and then I go sys, which is just a variable name I made up, sys, equals, I use the SS command, which stands for Statespace, okay? Not some Nazi shit. Yeah. So SS is Statespace, and what it does, it takes the A, B, C, and D matrices, and it forms this MATLAB object, okay? It's called a linear time invariant model, LTI model. And you can do a lot of cool stuff with an LTI model in MATLAB. One of the things you can do is simulate with that model, and that's what we're going to do. But there are a whole lot of options, and we'll explore some of those next semester. We'll encounter them, and they're pretty fun. Great. But let me just say that like this is, for me, like one of the biggest payoffs for MATLAB. Like using MATLAB is that MATLAB has a lot of tools for dealing with the state space model. And it's also one of the big payoffs for using the state space model technique, is that you can use MATLAB and similar tools very easily with that form of your system representation. So it's really, really helpful. Okay, so simulating the step response. The step input is widely used to characterize the transient response of a system. So you guys remember a step input, it's 0, and then suddenly it's some constant value for the rest of time. Okay? So the step input is what you guys were doing in the lab when you put a voltage in of, you had a duty cycle of like, what, 40% by default, and I think that the max voltage was like 20 volts. So like you're putting in like 8 volts, and then turn it off to 0 volts, and then 8 volts, and then 0 volts. So like those were step inputs, and then you turned them off at some point. So we're going to simulate this, and this is how you guys are going to predict what the output should look like. I mean, you could solve it analytically, but I think I would recommend just using what I've done here just to simulate what the response is. So the step input is widely used. MATLAB has a function called, you guessed it, step, that conveniently simulates the step response of an LTI system model. So this is literally all you have to do to simulate a step response, is to give it the system model that you just defined with SS, put it into the step function, and it will return the output matrix, which is to say an array that has columns that are the output vectors, and time array that it used to simulate the response. So if you do this, if you don't give step your own time array, which you can also do, then it's going to return to you a time array that it likes. And it's pretty good usually. Like, it does a good job of knowing like how long to simulate this system, so that you see all of the interesting stuff happen, but not too long where it's just simulating like the same steady response forever. So it does a pretty good job. But in a lot of cases, you're going to want to have your time array defined and then hand it to step. But I just went with the easy way. I let MATLAB choose the time array. And then I just printed a little. Okay, so I printed out the time array, the first 6 values of the time array. They're rounding a little bit in the last digit here, so this is why it looks a little bit not uniform. But and then the rest of these columns, the next 4 columns, so the next 4 columns are the first outputs. So the first 4 outputs. So this would be like Y1, this would be Y2, this would be Y3, this would be Y4. This is time, this column. And I just print out 6 of those too. So that was just to show you like what these objects are. Looking at these numbers doesn't give us a lot of insight, but having them, knowing what kind of objects we have in MATLAB is helpful. So the vector TA contains values of time, And array YSA contains a vector of time series values for each output. Remember, we chose as the output of our model to be like all the variables, right? Because we're interested in all of them. Because we're just very curious people. And I would say, you know, we're also pretty cool and good looking. I would just say we are. Since we're describing ourselves, we might as well just give you the whole picture. So if one would like the output for a step input, so US would be a unit step input, so if we scale it by a constant k, then it would just be any old step input. By the principle of superposition for linear systems, one can scale the output by k. So we haven't talked about superposition yet. We will the first week coming back from break, but generally one can say for a linear time invariant system, if you put in an input and, well, actually I'll say it this way, it's easier. If you scale the input by k, you can scale the output by k, and that will be a correct answer. If it's a nonlinear system, it doesn't apply. But linear systems, the ones that we're working with for the most part in this class, if you scale the input by k, you scale the output by k. So that's something we can do here. The step function only does a unit step input. So if you want to know what the output is for 8 volts input, you're going to want to multiply the result by 8. Yeah. Cool. So the outputs are plotted in figure 412. I just did a unit step input in this, but you guys are going to want to simulate for what your actual voltage input was. Okay? For your lab reports. So let's look at each of these responses. So the simulation just boom, ran, gave us these responses. Now we're going to look at it. What I've got here are each of the elements. So like the first graph is for J, the second one's for L. So the moment of inertia, the inductor, the damper, the resistor, etc. And then what I have is the left-hand axis, the blue axis, is the across variable. And the right-hand axis, the orange axis, is the through variable associated with that element. And we solve for all of them, so we can plot them both. And we'll do that. So we plot the angular velocity of the moment of inertia of J as it responds to the step voltage input. And notice that omega J starts off at rest and then it increases to some steady value. So if you put in some constant voltage, then you're going to get out some constant angular velocity. And it's in radians per second. All of these are in their base SI units. So that makes sense, right? You put in a voltage, it responds, it speeds up, right? It starts off at 0, it speeds up to a new steady state value of, it looks to be about 10 radians per second. Okay. The torque is what makes that happen, right? The torque that's being applied to that moment of inertia, to that flywheel, is what speeds it up. So you're going to have this torque increase here, and it's going to kind of peak, right? Because when you first turn on the voltage, it's going to have this sudden spike in torque. It's also going to have a corresponding spike in current as well, and so we'll think about that a little bit later too. So this is the response of the torque. So at first it's going to be applying a lot of torque, and then as it gets to its steady state value, it applies less and less torque. And then at the end, it looks like it goes to 0, but it's actually the torque at the end is a very small value. We're going to talk about what it is. It's actually going to be overcoming the bearing damping torque, which is small, but it's still going to be present in the steady state. So we're just trying to like dig into like get some insight into how like each of these elements is playing its role in the response of a motor to a step input. So the inductance, model as an inductor here, it has a current that starts off at 0 and it spikes early, just like the torque did, and then it drops off. So remember that an inductor has an elemental equation of dIL dt equals 1 over L VL, right? So the voltage, if you just solve for voltage here, is going to be effectively the derivative of the current. So it starts off positive and large, and then it drops. It drops, and actually it ends up going negative because the slope here, the current is dropping, so the slope is negative, the slope is reducing the current. So the voltage is, it's hard to read on this graph, but it's actually slightly negative, and it oozes back to 0. So that's what the inductor is doing. It's going to have this rush of current early, which is going to drive that torque, and then it's going to slowly dissipate away. It won't have more. Yeah?
So, how is the inductor working in the system? Because it's a DC input, right?
It is, but it's transient. So it's working because, and as you see out here, the current and the voltage are both 0 as we get to the end. So once it gets to its steady value with a DC input, the inductor is effectively not in play at all. It's just a conductor. It's just a wire. But its inductance plays a role when you're doing the transient response. So it only has an effect when the current's changing, right? Because that's what this equation says, the elemental equation. It says that when the current changes, there's a voltage across it. And that's when the inductance is playing a role. So when you first start it up, that inductance plays a role. But it doesn't later on. And actually, we're going to see when we look at the power and energy that what it does early on here is it stores energy when you first start it up, and then it releases it back into the circuit. And then when you get to steady state, it's not holding any energy. So it's a good question. Great. So then we look at the mechanical. So we went from mechanical flywheel over to the inductor. Now let's go back to the mechanical side and look at the bearing damping. So remember, the elemental equation for a bearing is that the angular velocity and the torque are proportional to each other. So the torque is going to be, it's a function of the angular velocity. The angular velocity is going to be whatever the flywheel angular velocity is. So this thing kind of just gets driven by whatever the angular velocity of the flywheel is. And the torque that effectively is going to be resisting the torque that's being applied from the motor, it increases, and it stays at some steady value. So this is going to be the torque that's left over, the torque on J. Let's see. TJ actually might go to 0, 0. Well, not exactly numerically, but this torque B is going to be offset by the torque that we're going to see. It's just barely hanging on down here, T2. Once again, you can't really see it, but it's a small torque. But notice that at high velocity, once we get up to that speed, or not really high velocity, but once we get up to speed, we're going to have a torque that is always impeding the motion, right? It's the bearing damping. It's never what you want. It's releasing heat. So, but we always have to deal with it. At low speed, it's not really in play, but when you get to higher speed, you end up with some torque that is impeding the flywheel. So then we have the resistance of the armature, so the windings, and we've got a proportionality between current and voltage again, as always. So as we have this current spike, the current of the resistor, the inductor, and the source, and the also the electrical side of the transducer, they're all the same, right? It's only one loop in the electronic side. So we have the same current, sort of early spike and then trailing off. So the resistance relates that to the voltage drop across the resistor, which has a similar spike and decay. Now, that means, so when you've got this current that flows through your resistor, we're going to be dissipating heat with that. It's I squared R heating, right? That's going to happen. So we're already anticipating early on we're going to be dissipating a lot of heat in the windings when we're starting it up. But that's going to die off because at higher, when you get close to steady state angular velocity, we don't have a lot of current flowing. So we don't expect to be dissipating a lot of heat in the windings. So that's good. So while the bearing started out not dissipating a lot of heat, it ended up dissipating more heat because we've got a higher torque here. The resistor has exactly the opposite characteristic, where at the low speed, high torque situation, it was flowing more current and heating up more. So we'll look at that a little bit more in the power flow graphs, and that'll help us there. So this is the one side and this is the two side of the transducer, right? So the ideal transducer that is just going to flow energy through it. So what it does is whatever voltage is applied to side 1 is in blue here. So it starts off at 0. It builds up to about 1. So it actually ends up following the source, right? The source voltage is going to go from 0 to 1 like at a step, right? It'll be 0, and then the source voltage will go to 1. Boom. And that's what the voltage 1 does, but it does it more slowly. It responds more slowly. And we'll, in fact, look at what the source voltage does down here explicitly. And then the current, of course, whatever current is going to flow through the other elements, we're going to see flow through the one side of the transducer as well. It's only one loop again. Then omega 2, so the 2 side, the mechanical side of the transducer, omega 2 is going to start off at 0 angular velocity. And it shares, remember, it shares the angular velocity with the flywheel. So it's going to speed up with the flywheel speeding up. And the torque that it is going to have is going to be proportional to the current that you're flowing. So the current is shown here. So we see this torque that's shown there. And the negative sign here just has to do with the direction of the arrow that we drew, which direction the torque is flowing. Okay. And finally, we have our source, our VS source. So remember, we said that it was going to have a step input, a unit step input of 1 volt. So that's what we've got in blue there that I just wrote over in black. And then, so that's set. And then how much current it flows depends on how much current is drawn from it. And that's what we see in the orange. We see this peak. And once again, that same current that we've seen in a bunch of these, all the electrical components, shows up here, and it all flows from the voltage source, which makes sense. Okay. Now we're ready to inspect the power flow and energy associated with each element. Since we have simulated both the across and through variable for each, we can compute the instantaneous power by simply taking the product of them at each time step. So if you know the voltage and you know the current at every time step, you know the power flow by just multiplying those two values. Moreover, we can cumulatively compute the energy contribution of that power for each element. For energy storage elements, this is the change in energy stored or supplied. For energy dissipative elements, this is the change in energy dissipated. And for source elements, this is the energy supplied or absorbed. And this is how we're going to compute it, and then we'll look at the plot in a second. I'll just highlight, I don't want to, I mean, this isn't a MATLAB class, but the more you see idioms in MATLAB, the better things will be for you. So this is me just pre-allocating. So I don't know if you guys talked about that in your MATLAB course, but it's more efficient usually to pre-allocate an array so that it's all stored in the same blocks of memory, and it doesn't have your reads and writes don't have to go back and forth across different addresses in memory. And then all this does is it takes the product of the across variable and through variable, which I put in order. I put across and then through and then across and then through, all the way through the outputs. So I just take the product of one variable with the next variable, and then this function, the cumulative trapezoidal integration function, is useful for doing a sort of numerical integration, and that's what I'm doing here. Is essentially a numerical integration. I have all the values that I want, and I want to cumulatively integrate them. So that's what I do, and that gives me the energy. So power and energy change. I print off a few values, but really what we want to do with this is plot it. So I left the plotting code out of the PDF, out of the notes, because the plotting code gets long and it's mostly just formatting stuff. But it is included in the source that I will upload to the website. So if you want to see how I do these plots, they'll be up there. So here's the result. So we get to see the power flow for this. So J is an energy storage element. It's an A-type energy storage element. And oh, I'm nice and frozen. So J is going to store energy and maybe release it to the circuit. We'll see. So power flow is positive, into the element happens early, right? So this is like when the current's flowing, when the torque is flowing. This is the power flow into J. This is like adding energy to J, to the flywheel. It's speeding it up, right? That's exactly what a flywheel does, is it stores mechanical energy by being sped up to some non-zero velocity. So we speed it up, we flow power in, and then as we remember that it stops speeding up as we go, right? Like we saw how the speed of the flywheel approaches a sort of steady state. So the power that we flow in is less and less. The torque that we're applying to it is dropping, and then eventually that drops to essentially zero torque. And what the result is of this is that we have this energy increase. We're just integrating the blue line here to get energy in orange. It accumulates, and we store it in the flywheel. So we store some energy in the flywheel. We're flowing it from the electrical side to the mechanical side, and we're storing it in the flywheel. Now, on the electrical side, we also have an energy storage element, a T-type, the inductor. And what we see with the inductor is an early spike in power flow into it. And that's when you first start flowing, so first apply this voltage to the circuit. You see this big spike. Remember, we saw the spike in voltage across the inductor. We see this spike in the power flowing into the inductor, followed by a long period of it's hard to see it from the graph, but a long period of negative power flow that slowly dissipates the energy from the inductor, not into heat, but back into the circuit, right? The inductor doesn't, in an ideal inductor at least, doesn't generate heat. It just flows the energy back into the circuit. So that's what the inductor does. It stores a little bit of energy at the beginning, and it releases it back in. And then by the end, as Robert pointed out, when you're in steady state and you have a DC supply, it shouldn't be doing anything. So it doesn't store any power or it doesn't store any energy when you're in steady state with a DC source. It just looks like a conductor. Yeah.
So is that kind of like damping the effect of the motor? Like it's kind of, because when you attach the voltage, it's like instant, and then this is kind of making it less of a shock to the system, or what is the inductor doing?
Well, so remember that, so if we could get rid of the inductor, actually we would. We would love to. But it's not actually a component we put in. It's an effect of having the armature coil windings. And we had to do the windings so we could get that electromechanical force, the Lorentz force to happen. We needed to create that magnetic field, and so that's what we needed to do. But we are left with this side effect of having this inductance because we have a coil of wire. And so actually it's a pain in the ass to have inductive loads. They're like they have a lot of problems. So this whole spike that happened early on, where we applied voltage suddenly, and we saw this spike in, where is it? We saw this spike here in the current flow, and then also the voltage. If you go the other way and you suddenly shut off the power you supply to your motor, there's a huge back voltage that gets generated in the windings, and that it can damage your electronics that drives the motor. Is usually what happens. Is it blows your driver. So inductive loads are kind of a pain. So if we could get rid of the inductor, we would. In this case, like, it's kind of nice because it does kind of have this effect of like storing a little energy and then releasing it back into the system, which is kind of smooths things out, like you point out. But in general, the inductance is a pain to deal with, and we don't want it, but we just have to deal with it.
So it's not actually a physical component; it's just the geometry of the component.
Exactly. So it's very much what we have described as a lumped parameter model, just like we might describe some actual like rigid body as being, it's like a point mass. Like in some instances, we could maybe make that assumption. That's what we're doing with this coil. We're saying, okay, it's actually this physical thing. It has a lot of properties to it. But we're going to say it behaves like an inductor and also a resistor. Because we don't put a resistor in there either, but there's some resistance associated with it too. So when we model it, we put them in, but when we actually build it, they aren't physically in there. They're just part of the coil.
So for the inductor, would it be the faster you can apply the voltage and the current, the less the effect, or the more gradual?
The more gradual, the better. If you didn't have to do anything quickly, you could just slowly ramp up your motor driver, and then you could slowly ramp it down. The inductive load wouldn't cause you any problems. But if you want to do something quickly, like suddenly, say, move a robot arm from here to there, you want to do it as quickly as you can, and so you're going to end up having the inductor come into play a lot in that sense. So the inductor comes into play if you ever had like in an AC motor, that would come into play with the AC signal all the time. For a DC motor, it comes into play in the transients, not in the steady state, but in the transients it does. So yeah, good question. Great. So we talked about the inductor, and it's releasing energy back into the system. Now let's talk a little bit about the bearing damping power. So this is going to dissipate energy, right? It's a bearing, so it generates heat. And so the power that flows into this thing is power that's dissipating energy. So it's the related to the speed of the damper, across the damper. And so the energy that you've dissipated is accumulated here. So at first you're not dissipating anything when you're not going in, when you not moving. But as you start moving, the damper is going to dissipate power. At a certain velocity, it's going to dissipate a constant amount of power, which still accumulates though, right? So at first this energy that it has dissipated was increasing rather rapidly, but then it starts to level out and it becomes linear. So after this, it continues to rise, the orange line, but it's linear. So you're always losing power. You're always, I guess would be better to say, you're always losing energy from your system into heat from the damper whenever you're going at a non-zero velocity. The opposite is true for the resistor. So when you weren't going fast, when you're just starting it up, a bunch of current was flowing, and you got a bunch of I squared R heat loss from your circuit. So that's what we see here. The power flowing out, and notice the difference in scale. So these are in watts. So we have 10 to the negative 3 scaling this axis. So at its peak, when it's going at its maximum speed here, it's not even 4 times 10 to the minus 3 watts of dissipation from the damper. It's going relatively slowly. We only put 1 volt in, so this thing is not going super fast, right? It's pretty slow. But then PR, the power that the resistor is dissipating, it peaks out here at 0.5, which is way bigger than this one peaks out. But what's nice is that it goes away, right? So as you speed up, remember the torque that you're applying is reducing, and so is the current that's flowing. So your I squared R drops off significantly, and you end up dissipating very little power in your resistor later on. So out here, it's actually not. Usually there's it goes to like a trickle, and you're dissipating just tiny amounts of power because you have a very small current. Only current that you have left in your circuit when you get to steady state is whatever current needs to flow to apply enough torque to overcome the little bit of damping torque, right? The damping torque is always trying to slow you down, so you always have to be opposing it with your motor. So if you have a motor that has, very little damping, you have like magnetic levitation, vacuum chamber, you get that thing going, and no current needs to flow in your power unless you have any dissipation. And if you have any dissipation, if you've got like rusty bearings, then you're going to have to be flowing a lot of current just to turn the thing at a constant speed. So there's that. All right. So notice there's always this trade-off, and I just want to really highlight this. We're damned if we do and damned if we don't, right? So at low speed and high torque, the resistor is going to be dissipating. At high speed and low torque, the damper is going to be dissipating. We're going to be dissipating no matter what. And actually, the worst is typically the resistor dissipation is usually the worst in a system. The heat that gets generated in your motor is detrimental, and it also consumes a lot of your power. So efficiency-wise and heat-wise, usually it's your windings that are the biggest problem. So cooling your motor to get rid of the heat is important. If you're going to be running it at a lot of high torque, high power in the electrical side, dissipation, but it still doesn't help you efficiency-wise. Efficiency-wise, it still sucks because you're dissipating a bunch of energy. So, and then we get to the transducer. So this is the one side, and this is the two side, the electrical side, and then the mechanical side. And what this tells us is, remember, these transducers, they don't store any energy, right? So whatever flows in has to flow out. So whatever power flows into side one, which quite a bit does early on, has to flow out of side two. And that's exactly what we see. So we see the power go in the electrical side and out the mechanical side. And so the energy that has flowed through levels out, and we see an exact opposite amount. So flows in side 1 and flows out of side 2. So that makes sense. And so these graphs have to be just symmetric, right? They're just the same thing but flipped. And finally, we have the source. So for the source, we've got the initial power spike when it's supplying a bunch of energy, per second, I guess, early on, and then it dies out. So this is when it's flowing a lot of current, and you get this peak in the power flow, and then the amount of energy that is supplied also increases rapidly, and then it sort of slows down. Once you get this thing up to speed, the amount of damping is not enough to make it so you have to flow a lot of power. So once you've supplied enough power to get it going, you don't need to supply a lot more after that. Until you want to speed it up more, then you would have to supply some more power. Or if you want to slow it down, you would have to supply negative power. Okay, estimate, which is regenerative braking. Oh, yeah, right? You guys heard of this term, regenerative braking? So cool. No time to talk about it, though. Okay, estimating parameters from the step response. Often, our model has a couple parameters we don't know well from the specs, but must attempt to measure. For the system under consideration, perhaps the two parameters most interesting to measure are the dominant time constant and the transformer ratio, TF, which is probably the most important. In this section, we'll explore how one might estimate them from a measured step response. Other parameters in the system could be similarly estimated. We're choosing TF and the dominant time constant. So this is what you guys are doing in the lab. Well, you guys are actually just doing TF in the lab. That's what you care about. And I'll show you how to back that out from data. Okay, so this is the part. This is the payoff for your analysis in the lab report. So what I do here is I do some symbolic A and B matrices, and then I use this SI minus A inverse B equation that gives me the transfer function, the transfer functions of the system to the state variables. The two state variables being omega j and IL. So the first value here in the answer is the transfer function from the voltage source to omega j, and the second one is the transfer function from the voltage source to IL. Remember, we're only using the transfer function here as a bridge to a differential equation, and so that's what we're going to use it for here. Here's the differential equation. We're interested in doing it in omega j. So we write the differential equation. It's second order, which makes sense because it was a second order system, a 2x2 A matrix, two state variables that we modeled originally in lecture 4.4. So that makes sense. And we've got our voltage source input. So the corresponding characteristic equation is given here if we're going to start looking at a solution, which has this solution for the lambda 1 and 2 in terms of our parameters. For a step input, that's just some constant value, and in zero initial conditions, the distinct roots lambda 1 and lambda, and for distinct roots lambda 1 and lambda 2, we're going to make that assumption and see if it's true. We have this solution for 17, which if you go back to the differential equation stuff, this is the solution you need. Let's compute lambda 1 and lambda 2 in MATLAB, and we get negative 16 and negative 374. So both of these values are real, which is important, and they're also distinct, so our assumption was correct. So we expect not an oscillation, but a decay to a final value. However, that decay occurs with two different time constants, right? So it's going to be an additive effect of two different time constants, one coming from this term, the other coming from this term. But the lambda, but let's look at these different time constants, the tau 1 and tau 2 corresponding to lambda 1 and lambda 2. If we look at them, we see that they're drastically different, a factor of over 22 different. So the second time constant decays, this one, decays really fast. So when this decays, this term essentially goes to 0, right? 0 quickly. And we're left with a single decay of an exponential function. And that is nice for us, since we're trying to do some estimation here. So the second one decays much faster than the first. That's good news for our estimation project, because we can easily ignore the step response's first 5 time constants, so about 13 milliseconds, and assume the rest is decaying at tau 1, which we call the dominant time constant, which we would look to estimate. Now, this happens so quickly, and in your data, this probably is just maybe like a couple points, so probably you don't even need to exclude those first couple points. I did just for completeness, so I lopped off the first 5 time constants. You can do that. But then the next thing that I do here is, so now what I have is an analytic solution with lambda 1 dominating it, right? What I did was I used all of the parameters from the spec sheet, and I said, okay, so this is what it would look like. This is what your curves should look like. That's the theoretical prediction of your curves. Then what I did is I said, okay, if we want to like pretend like I have data, I could have taken data from the lab, but I decided I wanted to teach you guys how to spoof data. So what you do, I mean, not to like for nefarious reasons, but so you can practice doing different things with it. It's very useful. So you add a little bit of Gaussian random noise on top of it, which I do in this step down here. I add a little bit of Gaussian random noise with rand n. And what I get is some noisy time response data. It's like, quote, data. It's not real data. It's spoofed data, right? So this approximates what you might see come out in the lab report for your measurement. And I'm going to try to do some data processing on that now and show you how to estimate from that the transformer ratio and the dominant time constant. So first we trim the data of the time constant, and then we use what we're going to do is we have to estimate the experimental time constant tau 1 and also the steady state value omega j infinity, which we're also going to need to find the transformer ratio. So what I do is I find the omega j infinity, the steady state value of the speed, by using this, this following sort of trick. So this trick, 5 easy steps. So what I do is I take the last, approximately the last time constant of this data, and I average it to give me my omega j infinity. And I do that because if you just took the last value in this noisy data, which is probably, I mean, it comes from a solution that is the best estimate of at the very last moment. It's closest to the steady state value, but since it's noisy, it's not a very good estimate of what that final value is. A better estimate would be to average a few points here. But if you keep averaging, you keep taking more and more of this, say you extended your average out to here, it's gonna be biased by this response. It's not even close to steady state here yet. So there's somewhere in between that's the ideal place. I say take the last time constant, which means you're within 1% of the final value. So that's what I do here. And I find that the final value should be around 10.18 radians per second. I take a standard deviation just for fun. And I say let's use the result, transform the data into its linear form. Oh, I don't just take the standard deviation just for fun. I take it because you guys need to do error bars on your graphs. So don't forget that. Okay, but there is a little bit of a problem. There is a little bit of a problem that we run into, and that is when we take the the estimate that we want to make, the log of mu steady state of the our estimate of omega steady state. When you do this, your idea is you're gonna flip this graph so that you can take the log of it. So you're gonna flip this. I guess it goes to 0, not -2. So you're gonna flip this, and you're gonna want to take the log of it because it's exponential, the decaying, and all that, and that's great. But what sucks is when you flip it, a bunch of these points up here, 33 to be precise, end up being negative down here. And then you try to take the log and it gives you a complex value. Can't do that. But if you just lop off all those points, you're going to bias your estimate significantly. So instead, what I tell you to do, like the quick and dirty way to do this pretty well, is to just lop it off for this estimate at the data point before you end up going above your steady state value. So that's what I do in the code. And so if that's hard for you to write the code, you can use my code. I don't care. And finally, I then can take the log of it. Then I get this nice linear fit of the transformed data. And I take the slope of the linear fit. -1 over the slope of the linear fit is my estimate of the dominant time constant, and it came out to be 0.0603, which is really close to what the original one was that we started with, right? I don't. What was it? Do you guys remember? 60.5 or something? 61.2 milliseconds. So really close with my estimate, and that makes total sense. Because I baked it in, right? That was we generated the data using that time constant. So I used all the parameters. But you guys aren't going to have the luxury of generating your own data. It's measured stuff. So you're going to be estimating variables that you don't know. So I baked it in. You're not going to be able to bake it in. Okay. Then I show you how to go from omega j infinity to TF. And that gives us an estimate of this transformer ratio, which is very close to the one that we baked in because we constructed it to be so. But your real measurements would yield an estimate probably further from the spec. So mine came out to be 0.0976. One of the spec sheets like 0.097 something else. And your estimates are going to be probably more different than this. But it shouldn't be that much different. Maybe like 20% would make sense different than this value. So that's a good check on your calculation to make sure it should be close to this. And that's really it. So any questions before we sign off? All right. Don't forget your